All right, so let's talk about decay. We talked about the half-life in SL, and we're going to keep talking about that, but let's talk a little bit more about what's happening, a little bit more conceptual, and apply that a little bit. Okay, so every time you have a population, it's got a half-life and it's decaying, and as it's decaying, the population is getting smaller. So as that population gets smaller, the decay rate gets smaller as well because there's less and less material there for it to decay with, and you get the famous exponential distribution that we talked about in SL. So we can represent this as this graph line, this exponential, as the current population, the amount of the current material that we have left, equals the original population times e raised to the minus lambda t. Lambda is the decay constant, and t is the time frame that this decay has happened. Now, as you'll see in different slides, sometimes t is equal to the half-life, and that makes things very interesting. And I mean that sincerely. It does make things very interesting. Okay. So the decay constant is not a universal constant. It depends on the material. And so sometimes you're either given it or you have to calculate. Okay. So here's a sample. Now, this is something that IB would expect you to derive. And they want you to derive, this is what they're basically saying, derive this equation right here. Okay, so we're going to start out with the equation that we just talked about. Okay, and then when t equals the half-life, this is what we start out with. Our current population is equal to the initial population divided by 2, because half-life, that means half of it is gone. Okay, so n is just n over n naught over 2. And so we substitute that in to this equation. So n naught over 2 goes over here. And look what we can do. We can cancel out the n naughts, and we end up with 1/2 equals e to the minus lambda over t. The capital T stands for half-life. Should be written in there, but it wasn't. All right, so next thing to do, let's just take the natural log of both sides. And we end up with natural log of 1/2 equals negative lambda t over 1/2. Okay, we move the negative over to this side. That's just a math trick. And so what we do, sorry, I was getting myself mixed up here. We invert this. What is, we take the negative out. To take the negative out, negative ln 1 over 2 equals ln of 2. And here you can see where we're about to solve our little problem here. And so the half-life is equal to natural log of 2 over the wavelength. I'm sorry, wavelength. Lambda in this case is the decay constant. So it's lambda, it's natural log of 2 divided by the decay constant. So if you know the half-life, you can figure out what the decay constant is of your material. Okay, so there's an example. Half-life of uranium-238, and that means 238 nucleons, is 4.5 times 10 to the 10th years. And for iodine-123, it's 13.3 hours. Find the decay constant for each of these. All right, so there's our equation that we just derived. We can bring it in. We know what the half-life is. It was given to us. We do not need to worry about the units unless we need to convert it for some other reason. But we can go with whatever units they give us. This equation works. So ln of 2 is 0.693. It's just a constant. That's just what it is. Divided by the half-life is all it is. Do the same thing for I-123. And there you see the decay constants that were derived for each one. So this is important. What you're looking at with the decay constant. The decay constant is a probability. It's the probability of decay of a nucleus per unit time. Okay, so it's the probability that so much of this nucleus is going to decay over a given time, and that's whatever that given time is right there. So if we converted this to seconds, then we would convert the probability to some other number per second. Okay, that's all it is it's just a probability.